Welcome. Today, we will be undertaking a comprehensive overview to understand the concept of power factor. In this section, we will introduce the key concepts of power factor and discuss its fundamental importance in electrical systems. Let's begin by defining power factor and its components. Power factor, or PF, is the ratio of real power to apparent power in an AC electrical circuit. 3:2 real power, represented as P, is the actual power consumed by resistive loads to perform useful work and is measured in watts, or W26. 3 reactive power, or Q, is the power that oscillates between the source and reactive loads, measured in voltamperes reactive, or VR. 26.2. Finally, apparent power, symbolized as S, is the total power delivered from the source. It combines both real and reactive power and is measured in voltamperes, or VA. 26.2. To better understand these components, we use the power triangle concept. 1. This provides a visual representation, geometrically illustrating the relationship between real, reactive, and apparent power. 8. Using a right triangle analogy, real power forms the adjacent side, reactive power the opposite side, and apparent power becomes the hypotenuse. 12. The phase angle, represented by the Greek letter phi, signifies the phase difference between voltage and current waveforms. 3. The power factor is then mathematically calculated as the cosine of this phase angle, or simply the ratio of real power to apparent cos phi ps 2.3. The importance of maintaining a high power factor cannot be overstated. A low power factor signifies inefficient use of available electrical power. 17. This inefficiency requires a higher current to deliver the same amount of real power, which in turn leads to an increased burden on generators, transformers, and distribution lines. 3. Furthermore, a low power factor can contribute to greater voltage drops and potential instability within the entire electrical system. 16. Several factors contribute to a low power factor. The primary causes are inductive loads, such as electric motors, transformers, and fluorescent lighting ballasts. 9. 16. Additionally, equipment that is underloaded and operating below its optimal capacity often draws excessive reactive power. 16. Nonlinear loads, common in modern electronic devices, can also degrade the power factor by introducing harmonic distortion into the system. Fortunately, there are effective methods for power factor correction. The installation of shunt capacitors or capacitor banks can supply reactive power locally to counteract inductive loads. 23.7. For larger industrial applications, synchronous condensers, which are overexcited synchronous motors, can be used to generate leading reactive power. 23.22. Additionally, active power factor correctors provide electronic, dynamic, and precise control to optimize the power factor. 7. Improving the power factor yields significant benefits. It leads to cost reduction by avoiding utility penalties and lowering overall electricity bills. 5. By reducing the total current required, it enhances the available power capacity within the existing electrical infrastructure. 17. This also results in better voltage regulation and reduced fluctuations across the system. 4. Ultimately, the decreased operating currents lead to less thermal stress on equipment, extending its operational lifespan. 15. In summary, we have recapped the definition of power factor as a crucial metric for AC system efficiency. We've recognized the significant operational impacts of a low power factor on electrical networks. We have also explored effective correction strategies to optimize it. By implementing these strategies, we can appreciate the significant economic and operational advantages that come from maintaining a high power factor.